What's up guys, welcome back to the channel. In this particular video I will explain the problem mother vertex. This problem is really interesting guys, and believe me, if you watch this video till the end then you will have complete idea about how this problem can be solved. Starting with the problem statement, so it says that you are given a directed graph and your task is to find a mother vertex in the graph if present. Now, what is a mother vertex? So it is also given here. A mother vertex is a vertex through which we can reach all the other vertices of the graph. Okay, now an example is given here. Let me explain the problem using the given example. So guys, you can see that we are given a graph and our task is to find a mother vertex, right? So what I can do is I can start with 0. I can check whether 0 is my mother vertex, and if it is not, then I will go to 1. I will check whether 1 is my mother vertex, and after this, if 1 is not the mother vertex, then I can check 2, and this way I can check out every particular vertex, right? And if I have found any mother vertex, then I'll simply return that particular vertex, and if there is no any mother vertex, then I have to return -1, right? That's why it is given here. Only if present you have to return the mother vertex. If not, then you can simply return -1, right? Now guys, let me start with this particular example. See, I'm simply going to start with 0, and from 0 you can see that I can visit 2, right? I can even visit 1 as well, because from 0 if I go to 2, then I can simply go to 1, right? So from 0 I can go to 2, I can go to 1, and I can even go to 3, right? And I can also go to 4. So from 0 I'm able to visit every particular vertex, right? So guys, for this particular example, 0 is going to be the mother vertex. You can see the output as well. Now I hope you have got the clear understanding of the problem statement. So let's talk about the solution now. Okay, so I have written one example here. And guys, after looking at the problem explanation, the first approach that will come to your mind is quite similar to this one, right? We can check out every particular vertex, and for each vertex, we can check if it is a mother vertex. So if it is a mother vertex, then we can simply return that particular vertex. And if there is no any mother vertex, then we can simply return -1, right? This is the approach that we are going to follow. This is the first approach even that we have, right? So guys, see. Still, we have something that I have not answered. The question is how I am going to check for a particular vertex if it is a mother vertex, right? How we are going to check? This is the question that we have. So let me explain, guys. First of all, I am going to write a loop because we have to check for every particular vertex, right? So I'll start with the first vertex, then I will move to other vertices, right? So guys, I have a loop here. Inside this loop, I will check if the given vertex is a mother vertex. Let me explain how we can check. So see, I'm at 0 currently, right? And from 0, I can simply perform any kind of traversal, whether it's BFS or DFS. I can perform any traversal, and while performing traversal of the graph from a particular node, if I'm able to reach every other node, then I can say that this is a mother vertex, right? Because I'm just looking for a path, right? I'm just going to visit every particular node. So from 0, you can see that we can visit 0 and we can visit 1, but we cannot visit 3. So this is the approach that we are going to follow. So let me use DFS, guys. So I'll simply perform DFS. I have to start with I, right? I is whatever node we have. So initially we have 0, then we will have 1, then we will have 2, right? This is how we are going to check every node. So we will have a adjacency list as well. Adjacency list I have already explained in the previous video, guys, right? After this we have a visited array, and this visited array will tell me whether I am able to visit every particular node from I or not, right? And now once I have performed DFS, then I will simply start a loop. So I'll start a loop for j equals to 0, then j is smaller than v, then j plus plus, right? What is the use of this particular loop? So inside this loop, I will check if every particular node is visited, right? So if visited, if visited of I equals to true, right? If visited of I equals to true, then I can simply have a count. I can make a count, and this count is going to keep track of all the true values, right? And so I'll do count plus plus. This is a kind of pseudocode, so you can initialize count with 0, and after this, if my count is equal to v minus 1, only that particular case I can say that the current vertex is a mother vertex, right? This is about the brute force approach, guys. I just want you to give the idea about how the brute force works, right? So what is the time complexity of this approach? So time complexity of this approach is O of V because of this. Then we have one more loop, one more traversal inside this, and we have one more loop, right? So the time complexity for this particular code is going to be O of V cross V plus E, right? This is the time complexity. So guys, now you can see that this particular code is not going to work, right? This has a greater time complexity, so it will not work for larger inputs that we are going to have in the problem statement. And justifying the time complexity, so this is the first loop that we have. This is O of V, right? This is O of V plus E because this is a DFS, and this is nothing but O of V again, right? So time complexity, because these two loops are like not nested loops, so time complexity is going to be a greater value of O of V cross V plus E or V cross V, right? So we have this as the greater value, so that's why I have written time complexity like this. Now guys, this is about the brute force approach. If you want to note this down so you can note it, I am going to explain the optimal approach now. So first of all, let me erase everything that I have written here, guys. So I am going to erase everything from here so that I can get some space in order to explain the optimal approach, right? Let me erase this. It is going to take some time, guys. So let me erase everything from this particular window. Uh, okay, so now let me raise the time complexity as well. Okay, now let me explain the optimal approach, guys. First of all, let me raise this as well because I want a clear view of the graph so that I can explain you better. Okay, now guys, see, for the optimal approach, we are going to assume already that the first vertex is going to be a mother vertex, right? So we can assume that 0 is the mother vertex. Let me represent 0 with a variable which is answer, right? So I'm going to store 0 in the answer because I'm assuming that this is the mother vertex, right? So now I will start performing DFS from 0, right? So I have to start a loop again because in undirected graph we start when we perform DFS, guys, so we start a loop, right? We start a loop for I equals to 0, then I smaller than V, then I plus plus, so that we can perform DFS for the whole graph. Because if I perform DFS from any particular node, then there is a possibility that some node will be missed, right? This is the only case when we have a disconnected graph or a directed graph, right? Now guys, see, this is how we can perform DFS. So what I'll do is I'll simply check if okay, if my current node is not visited, right? So I need a visited array as well. If visited of I equals to false, right? Only in that particular case I'll start performing DFS from that particular node. So what I'll do is I'll make a visited array as well. Visited is currently storing false for every value. So I have false, right? So see guys, I'm assuming that 0 is my mother vertex, so I have to check 0 for 0, right? And for 0 this condition is true, so I'll simply perform DFS from 0, and I'll write I here, then I'll write adjacency list, then I'll write visited, right? Now see what happens when we perform a DFS from 0. I have 0 first, so let's say this is my visited array. So in the visited array I'll simply add 0. After this I will go to this 2, right? So I'll simply add 2 in the visited array. After this I will go to 1, so I will add 1 in the visited array, and after this I will again go to 0. So DFS from 0 is done, guys. You can see that I have visited every node from 0, right? So till now I have visited 3 nodes and I am done with DFS from 0, right? After this I will go to I equals to 1, and for I equals to 1 you can see that this is already visited, right? So this condition will not be true, so I'll not perform DFS from 1. After this I will go to 2. You can see that 2 is also visited, right? So I'm not going to perform DFS from 2. After this I will go to 3, and guys, there is something that we can observe. See, from 0, when I performed DFS, then I visited 2, 1, but 3 was not visited. Even because only if 3 is not visited, only in that particular case this condition will be true. So I will say that okay, 0 is definitely not going to be my mother vertex, right? There is a reason, because from 0 I cannot visit 3, right? So 0 is definitely not going to be the mother vertex. So at this point, guys, I have to assume that this particular node, which is the current node, is my mother vertex, right? Of course there is no any guarantee, but we can assume. So what I'll do is I'll simply say that okay, now I can assume that the current vertex is my mother vertex, so I'll simply change answer equals to I, right? Guys, this is what we are going to do. Should I need to should I have to write the code for DFS as well? Let me write the code for DFS, guys. So I'm going to write the code for DFS. I have I, then I have adjacency list, then I have a visited array, right? What we do is we simply first visit the particular node that we have. So I have I, right? So I'll simply visited I. Visited of I will become equals to true, right? After this, I will check out every neighbor of the current node that we have. So I will check the adjacency list for neighbors, right? So I'll say that for every element in adjacency list of I, right? This is how I will check. And if that particular element is visited, if my visited of EL equals to false, right? Only in that particular case, I am going to call DFS again, right? I will call DFS again. This is how we perform DFS. I will call DFS from element, right? And I have adjacency list as well, and I have visited array as well. So guys, this is the approach that we are going to follow. And see, when we are done with every particular node, so you can see that from three I have performed DFS, and then this 3 is also visited, 3 is also visited, and 4 is also visited, and now I am done. And when I have performed DFS, then what is the last node that we have in the answer variable? So this is the last node, right? So guys, see, as I said, there is no guarantee that this particular node is a mother vertex, right? So we have to check manually. We have to check manually. What we are going to do is from this tree, we are again going to perform DFS. So I will perform DFS from the answer variable that we have. So answer. Even I think it makes more sense if I use a last node variable here, right? So let me use a last node. Why I am saying last node? Because this is the last node that we have while performing DFS, right? So I'll write last node here, and instead of writing answer, I'll write last node here, right? So I'm performing DFS from last node. I'm performing DFS from last node. I have ADJ here, I have visited here, right? And after this, guys, I will check my visited array, right? So if visited array is able to visit every particular node other than this 3, then I can say that 3 is my mother vertex, right? So what I'll do is I will first empty the visited array, right? So I'll say that, okay, fill visited array with false again, right? After this, I will perform DFS. So I will write a loop again. Guys, you can note this particular code if you want to note this code, because I'm going to scroll down, right? After this, I'll simply uh, check my visited array, right? So I equals to 0, I smaller than b, then I plus plus. If my if my visited of I is equals to false, then it means that we are not able to visit that particular node, right? So I'll simply return -1. And else, if we have visited every particular value, then I can simply return okay, I can return last node here, right? Because last node is basically storing the mother vertex that we have. So guys, this is all we need to do in order to solve the problem. I hope you have got the intuition and approach, right? Talking about the time complexity, so we are only performing DFS, right? So the time complexity of this particular approach is O of V plus E, because we are only performing DFS, right? After this, okay, there is a question that may come to your mind is, see guys, while performing DFS, what is the optimization that we have done? We have not checked this one and this two, right? We have avoid checking this one and this two, and even this makes sense. Let me explain why. So when we started performing DFS from 0, then we have already visited this 2 and this 3, right? And there is one thing that we can observe, that if from 0 we cannot visit this particular node 3, then definitely from these two nodes we can again not visit this 3, right? So there is no sense of checking these two nodes, because you can see that these two nodes are in the path from 0, right? And if from 0 I am not able to visit 3, then from these I can also not visit 3, right? Now guys, I hope everything related to this problem is clear to you. Let me show you the code implementation. So uh, okay guys, so this is the code that we have. Let me show you the C++ code as well. So okay, let me show you the C++ code. Okay, this is the C++ code, this is the Java code, this is the Python code, and we have the Java code as well, right? So see guys, this is the main DFS function that we have in Python, and this is the DFS function in C++, right? After this is the main approach that we have, guys, because DFS is something that is a very general algorithm, but this is the main approach that we are going to follow. See, first of all, uh, we are initializing last node with 0 because we are assuming that 0 is our mother vertex. Then we will verify it, right? So while verifying, guys, if there is a case that I'm not able to visit any particular vertex from 0, then I will simply change my I will simply change my last node, right, or my answer, because now I'm going to assume that current node is my last node. And after this, as there is no any guarantee that the current node is the last node, so I will verify it, right? I will first fill my visited array with false, and then I will perform DFS. Then I will verify if the current last node is actually a mother vertex, right? Similar approach we are following here as well, guys, and here as well. The only difference is of syntax, right? This is the code in Java. Now I hope you have understood everything related to this problem.